I'm pleased to introduce today's two speakers, Dmitry Darushkin, who's the Director of Technology for Subsurface Dynamics. He's based in Calgary, Canada, and Dr. Jeremy Gallup, who is the VP of Services for Icon Science, and he's based in Houston, Texas. They're going to discuss our solution to shut-in reactivation strategies. The webinar today discusses a collaboration between Icon Science and Subsurface Dynamics. Icon Science is a geoprediction company that helps operators better understand the reservoir. We do this with a wide range of specific service work, and all the work is done on Icon's world-famous RockDoc and iPoint software. So with pleasure, I'll hand it over to Dmitry.
Thank you, Barry. Subsurface Dynamics is an independent advanced reservoir engineering firm, primarily focusing on completions and production optimization. We are successfully solving today's most complex challenges for unconventional operators, such as parent-child interaction, completion design optimization, pressure sink mitigation strategies, shut-in reactivation strategies, and of course, defensive fracs. We have experience operating in over 20 international jurisdictions with average delivered NPV increase of 20% and up to 20-fold in increased production to our clients. And let's get going. Icon Science and Subsurface Dynamics have joined forces to solve a wide range of problems for unconventional operators, and have developed a joint solution by integrating advanced reservoir characterization and geomechanics with advanced reservoir engineering. The main goal of this technology is to solve shut-in reactivation damage, detrimental frac hits, underperforming child wells, pressure depletion impact and damaged parent wells, and overstimulated reservoirs and CAPEX overruns. But today, we would like to focus on one specific topic and discuss in more details the shut-ins and dive deep into this topic. In this time of market volatility, some operators will be forced to shut in some of their wells. The question becomes which wells to shut in and how to minimize the damage and lost production after reactivation. SSD and Icon developed a solution to answer those questions. Which wells and pads are safe to shut down, and what are the main criteria for selection? How can we quantify it, and with what level of confidence? And what is the optimum reactivation drawdown management plan? And of course, economic forward modeling of reactivated well, which becoming more and more important for the majority of operators on the market. So first, let's decide which approach should we use. Since we're dealing with extremely complex systems where we have various stresses, fracs, depletion, different completion technologies, and complex reservoir fluids, the best strategy would be to employ a physics-based approach. The key benefits are that we model key drivers and actual physics of the process rather than correlating only a few data points. This approach will require very little historical data for calibration and will solve the problem of a lack of data on shut-ins. As we all know, broad shut-ins are new and very little historical data is available. Previously, we only shut in wells if we had any operational issues or anything went wrong in the field, and nobody really knows these days what will happen if we shut in for a long period of time. And last but not least, physics-based models have extensive predictive capability, which is exactly what we need, and can be performed efficiently and cost-effectively. Since we established that a physics-based approach would be an optimal solution, let's define what needs to be done to perform a full shut-in reactivation loop. And let's start with a simple diagram on top and go over the major steps. So first, we need to model the physics of the process to understand those processes. Then we need to correlate the physics to field examples to calibrate the data set. Then we need to find and identify main driving mechanisms. And after that, we can grade our wells using those driving mechanisms and criterion to select the perfect candidates. And as a final step is to go ahead and execute it in the field. It's pretty simple at the first glance, but to capture all those mechanisms with any level of confidence, what we should do is perform advanced geomechanical and stress modeling. We need perhaps to history match existing production and pumping schedules for flow and frac geometry. We need to estimate geometry and magnitude of the depletion and stress changes if we have a child well, second generation, third generation child wells. We need to model the actual shut-in period, and only after that we can perform reactivation optimization, pin down those selection criteria for shut-in candidates, and as a final step, perform the economic modeling for the whole loop. So as you can see, it's pretty science and labor-intensive process, even though it seems to be fairly simple from the basic diagram. And now I'll give the word to Jeremy.
Yeah, thanks, Dimitri. We're talking about drivers and mechanisms, but what are the primary suspects that can cause damage and detrimentally affect our production? Changes in the subsurface effective stress field will occur that are coupled to the pore pressure changes after shut-in. Around your hydraulic fracs, like the picture shown, this may introduce shifts in the proppant pillars. The speed of stress changes are linked to the initial magnitude of depletion when producing the well, and also the matrix permeability and clay content that controls the pressure diffusion. The presence of natural fractures would also affect the speed of the pressure changes. Differences in pore pressure may lead to crossflow during the shut-in, from frac to frac, well to well, or bench to bench. The reservoir fluids present, especially water, will impact the subsequent restart and may affect the wellbores themselves. The drawdown management plan will also have an impact. How is it initially produced and how should we reactivate it? Should we choke the well or let it flow? How do we do it? The core paradigm for both subsurface dynamics and ICON is really to model the actual physics. Broadly speaking here, we see two loops in this figure. The left-hand loop representing the static input modeling and the right-hand side representing the dynamic modeling, all with feedback occurring. We need to address the subsurface stresses and the rock mechanical properties through petrophysics and rock physics. This is followed by 1D stress modeling integrated with the 3D seismic inversion. We can then construct an advanced 3D geomechanical model and feed it into the dynamic simulation. Since every field will have depletion and fracs, we will need to perform history match of flow and fracs to estimate frac geometries and fractures and depletion halos. And then we can reverse the process and carry out forward modeling, forecast the shut-in period to see what actually happens to fracs and pressure within the reservoir and what are the key driving mechanisms. So I'll talk a little more detail about the components on the left-hand side of the workflow, which represents the static input modeling. Static modeling should use all the available data to minimize the subsurface uncertainty when diagnosing well production. More uncertainty will lead to less complete understanding of the well effects. The data to be combined spans a range of scales. We incorporate core data such as XRD and pyrolysis for mineralogy calibration, well logs and petrophysical analyses, defits and stress measurements, and 3D seismic data through inversion. All of these are subjected to rigorous statistical calibration to provide the best 3D volumes of petrophysical and geomechanical properties that can be used as input for dynamic modeling. The workflow progresses from left to right, taking core and log data and carrying out rock physics and petrophysical analysis in the flow chart we see at the top. The elastic data can then be fed into a 1D geomechanical analysis, matching to observed borehole deformations. In parallel, the elastic data can be used to tie the 3D seismic data to parameterize the inversion. The seismic inverted data can then be combined with the 1D geomechanical models to produce an advanced 3D geomechanical model that can represent the pre-drill stress state. In addition, the elastic data rock physics relationships can be used with the seismic inversion to create 3D cubes of reservoir petrophysical properties that can be used in flow simulations. Now let's jump back to see what happens within the reservoir, the dynamic reservoir modeling. So I'll pass it back to Dimitri here.
Thank you, Jeremy. With support of advanced geomechanics, the next step is to address all the changes that we imposed within the reservoir during completions and production periods. This means we have to history match fracs to actual pumping schedules to recreate the actual geometries. We have to history match wells to production history to understand geometry and magnitude of the depletion. And we have to model associated stress changes and quantify this change. This slide illustrates the full complexity of the problem. Look how much action is going on within one pad only. So we have a multi-bench development, we have parent-child wells, we have depletion, we have different completions technology, and so on. So it will be extremely hard to capture all these changes using data analytics methods, let alone trying to understand what the key drivers are. And therefore, a physics-based approach becomes a key to understanding and capturing this complexity. So after we've done all the preparation work and we established the type and magnitude of changes that we induced within the reservoir, we can finally move to the main stage and start optimizing shut-in reactivation strategies. What should we anticipate and what should we be looking for? If we have a multi-bench development, we need to look at how benches will interfere with each other. Did we connect them when we initially completed them? How they were developed? Which technologies we used? How extensive depletion is? And what type of flow do we observe on the production curve on our wells? Then how much stress do we impose on fracs during shut-in reactivation and how it will affect the proppant pack? Will this stress change be high enough to shift the proppant grains and to cause detrimental effect on conductivity? And last but not least, what is the optimum reactivation strategy and what will be the best drawdown management plan that we need to use to maximize production and minimize potential damage? All these questions needs to be answered before we can proceed with actual shut-in execution. So now let's look at the field example and try to interpret the production profile and effects we're observing during the shut-in. The green curve shows historical data, the dotted line shows type curve, and the purple line is showing anticipated production if there would be no damage. So this particular well was shut in only for 4 months. That is represented by the break in the production profile. So the red colored area is highlighting the lost production. In other words, if there would be no damage, our well would come back online at the purple curve, which is not the case. And in real life, it comes back online at a significantly lower rate. So under the regular circumstances, it would not be a big deal if we have only one underperforming well. But imagine if you have 100 wells like this that are coming back online with much lower rate, that would be quite a disastrous outcome and compounded with the time value of money, it can significantly impact your assets economics. So as a result, our main goal and main challenge these days is to find the way to bring the well from green curve to a purple curve through optimization and identification of the key drivers. We believe that our solution can identify the optimum risk mitigation strategy and maximize production as it's shown on the plot on the right top side of the screen, where each bar represents different scenarios versus EUR, And as you can see, by using different strategies, we can affect well behavior quite significantly and find that optimal scenario that we need. So what do you get from this study as an operator? So science is good, but we also want to have something we can readily implement in the field. That's why we have designed studies to produce a solid execution plan, which will contain the following deliverables. So first and most important are critical selection criteria and key drivers to select best candidates for shut-in within your asset. Then the maps with graded impact, or which areas will have minimum or maximum impact from shut-in that you can readily use for execution. You can see a simplified example on the background of the slide. Then 3D zoned volumes for reservoir and geomechanical properties, which can be used in integrated modeling and integrated studies internally, production forecasts after reactivation, and of course, economic evaluation. So overall, it's a well-rounded, detailed execution plan that can be easily implemented in the field. And to conclude, using today's technology, we can successfully model and predict the detrimental effects of long-term shut-ins on existing frac geometry. How? Through physics-based modeling. By using SSD and ICON, operators can successfully forecast and reduce shut-in damage by up to 20% in future produced volumes. And by using our solution, operators can make informed decisions on which pads are preferential for shut-in and what are the key drivers. We would like to invite industry members to get ahead of the curve and contact us to initiate the study. And the faster we can address these issues, the better economics we can get. And we would also like to stress out, if you already shut in your wells, it's not too late to intervene and mitigate the risk to optimize your strategy. Thank you for your time. I hope you liked the presentation.